In this video, I'm going to go through some selected problems. Ooh, that's a bad marker. From review 2, kind of like one of each of the types of problems, starting with the big boy number 1, a system of 3 equations with 3 variables. So the strategy is, I'm going to number these equations. I'll call them 1, 2, 3. And you want to somehow add these equations to eliminate one of your variables, and then add a different 2 to eliminate the same variable. So I'll show you what I mean by that. I'm looking here at my x terms, and I think it'd be pretty easy to get some of those to cancel. I noticed that if I take my bottom equation, number 3, and I multiply everything by 2, that coefficient for x would be minus 2x, and when I add it to the 2x, it would be eliminated from the equation. So I'm going to take equation 2, I'm not going to make any changes to it, and I'm going to take equation 3, multiplying that 2 to every part of my equation. So make sure you're being very careful there. Now, with this in mind, I'm going to add them. 2x plus a negative 2x is 0x's. That's the whole point. I wanted to eliminate one of my variables. 1y plus 4y is 5y. And 3z minus 10z is minus 7z equals 34. So that's my first equation. Now I'm going to take, let's say I'll take equation 1, and I'll work with equation, let's say number 2, because I already used equations 2 and 3, so it just needs to be a different pair. I could do 1 and 2, or I could do 1 and 3. Let's take a look at 1 and 2, and to get my x's to cancel there, I'd have to multiply that second equation by negative 2, so that the coefficient in front of x would be negative 4. So keeping the first equation the same, to make that, let's see, 4x minus 3y plus z equals negative 10. Then if I distribute the negative 2 to the second equation, that would be negative 4x minus 2y minus 6z. 0 times anything is still 0. So make sure you're being very careful as you're going through that. And when I add these next two equations, my x's cancel again, and I get negative 5y minus 5z, 1z minus 6z, equals 10. So these are my 2 equations I'm currently, oh, look at that, I almost made a mistake. That's a negative 10 there. I should have wrote that a lot bigger. That should be negative 10 there. But these are the 2 equations I'm currently working with. I've got minus 5y minus 5z equals negative 10, and I've got 5y minus 7z equals 34. Now, depending on what your coefficients are, you might have to multiply one of these equations by something to get one of your variables to cancel. But I noticed my minus 5y and positive 5y already would cancel if I added those equations. So I'm going to add minus 5y and 5y to get 0. Minus 5z minus 7z would make negative 12z altogether. And negative 10 plus 34 is 24. So if I divide out the negative 12 on both sides, in most cases you get integer answers. So I find that z is equal to negative 2, right? A positive divided by a negative is negative. That's the hardest part, just getting one of your variables. Once you figure out what one of your variables are, you can plug into either of your smaller equations to solve for your second variable, and then plug into your originals to get your last one. So I'll pick, let's say, this 5y minus 7z equals 34. So to get y, I'd substitute in negative 2 for z and solve. So negative 7 times a negative 2 would be positive 14 equals 34. And if I subtract 14 on both sides, I get 5y equals 20. And if I divide out the 5, I find that y equals 4. So already I've got 2 out of my 3 variables here. Now I just need to solve for x, so I could plug into any one of these original equations I'll plug into the second one. Doesn't matter which one, whichever one looks easier. I'll substitute in 4 for y, and I'll substitute in -2 for z. So if I simplify here, 3 times -2 is -6, plus 4 is -2. And if I solve this equation, I find that x is equal to 1. So those are my 3 solutions, and you can plug them back into your original 3, and it should satisfy all 3 of those equations for x, y, and z. And sometimes you'll see your answer written as an ordered triple, where it's an x value, comma a y value, comma a z value. So the difficulty here is just making sure you don't make any small arithmetic errors, like me and that -10 up there. That's going to happen when you go through these. So try to be as careful as you can as you're combing through these. All right. Let's take a look at number 3. This is a substitution problem where I want to solve for one variable in one of my equations. So I notice in my bottom equation there, if I add 2y to both sides, I'd isolate x. And then I'm going to take that value for x and substitute it in for x in my other equation at the top there. So I'd rewrite that as 2y plus 9 instead of x, minus 3 squared, plus y minus 2 squared equals 25. So all I did was rewrite that top equation, but instead of x, I made it 2y plus 9. Now, the whole benefit of that is that in this equation now, there's only one variable, so I should be able to solve it if I simplify a little bit. First thing I notice is that 9 minus 3 is positive 6. So I could just rewrite that as 2y plus 6. And now I'm going to double distribute. A binomial squared means write it twice and distribute and combine like terms. So this one's going to be a little bit more algebra because there are 2 binomials to distribute. 2y times 2y is 4y squared. 2y times 6 would be 12y. 6 times 2 would be 12y again. And 6 times 6 would be 36. Oh, if I keep going, y times y would be y squared. That's a plus linking them. Y times a minus 2 is minus 2y. Minus 2y. And a minus 2 times a minus 2 is positive 4. So I've got this big long equation with lots of terms to add up. I notice I've got 4y squared plus 1y squared would be 5y squared. 12y plus 12y is 24y. Minus 2y would be 22. Minus another 2 would be 20y. And then 36 plus 4 would be 40. And this is the equation I have here. So this is a quadratic equation because the highest power of a variable I see is 2. So the strategy is get one side equal to 0, and then hopefully I could either factor, or if I can't, I'll use the quadratic formula. So I'll minus a 25 on both sides here to get 5y squared plus 20y plus 15 equals 0. Now remember, the first kind of factoring you should always look for is the greatest common factor. And lucky me, there is a GCF of 5 in all of these terms. So I'm going to factor it out to make this y squared plus 4y plus 3 equals 0. And it looks to me like that trinomial factors even further using an AM method. I want to find numbers that multiply to positive 3 but add to positive 4. Well, I can only think of 2 numbers that multiply to 3. That's 3 and 1. So if I set each of these equal to 0, obviously 5 is never going to be equal to 0. But if y plus 3 equals 0, I find that y equals -3 is a y value that satisfies this equation, or y equals -1 would be another value. But consider how many variables you started with. In my original equations, there's both an x and a y, so as a final answer, I should have 2 x values to correspond with these y values. Now, when you plug back in, it doesn't matter what equation you plug back into. I notice if I plug into that equation highlighted in purple, it would just give me the x value immediately, so that's the one I'm going to do. So I got to plug in y equals -3, and I got to plug in y equals -1. If I plug in y equals -3, I have x is equal to 2 times y, which is -3, plus 9. 2 times -3 is -6, plus 9 would be 3. And if I plug in -1, I'd find that x value is 7. So as ordered pairs, my first one would be x equals 3, comma y equals -3. And my next one would be x equals 7, comma y equals -1. And these would be my two solutions for this particular system of equations. Remember, it represents where my graphs would cross if I were to plot these in the coordinate plane. So you should always have x values and y values. Most of the time there's a pair of them. Sometimes if your graphs only intersect once, like if you have something like this where they only intersect once, you might only get one ordered pair, but it depends on the scenario. So for number 7, what are the roots, or what are the solutions to the system below? Remember, the solutions to a system of equations, just like in the last example, are where the graphs intersect. So they intersect at x equals 1, that looks like, and x equals 6, but I need to represent those as coordinate pairs. So when x equals 1, the y value for both of those points is -4. And when x equals 6, the y value for both of those graphs would be 1. So those are my two intersection points for the graphs. So they represent the solution to the system of equations. Number 8. Find the roots of the following equation in simplest a plus bi form. Well, if I'm looking at a quadratic and they're asking me to put it in a plus bi form, chances are I need to use that handy-dandy quadratic formula. Remember, that's for any time I have a quadratic equal to 0. Like if I add the 7 over there, and I can identify an a value, a b value, and a c value, I could substitute into the quadratic formula. X equals -b plus or minus the square root of b squared minus 4ac all over 2 times whatever a is. You'll get that on the reference sheet. You don't need to memorize that. You just need to know how to substitute into it. So, if I start plugging in, x equals -b, which is 2, plus or minus the square root of b squared minus 4ac, all divided by 2 times a. Now, this is mostly a calculator problem. I know 2 times 3 is just 6. What you're going to do is you're going to type this in to your calculator without the radical. Exactly how you see it there. 2 squared minus 4 times 3 times 7 with parentheses and all. And your calculator should say that that number simplifies to -80. And that should confirm a clue you had in the beginning of the problem. I wanted it in simplest a plus bi form, so there should be some imaginary number here or some negative under the radical. At this point, it's a simplification problem. So what I'm going to do is I'm going to take this radical -80, and I'm going to ask myself, how can I simplify this? The first thing I notice is that there's a negative under the radical, so I could pull that out as an I, and think about how to simplify radical 80. That's all a negative under the radical means, just that there's an imaginary number there. So if I split this off now, I want to find the biggest perfect square that divides into 80. Remember, your perfect squares are like 4, 9, 16, 25, 36, and so on and so forth. So you could test out a couple of these in your calculator, but you want to find the biggest one. Yes, 4 divides into 80, but 16 is the biggest one that goes in. And it goes in 5 times. And you could do that by guess and check, or you could use your calculator. But the whole reason we're doing this is because radical 16, we know what that is. It's 4. So, as a final simplification, radical -80 can simplify to 4 times I times radical 5. It doesn't matter what order you multiply these things in. I know it says a plus bi form, but if you put the I at the end, sometimes it looks like maybe it's underneath the radical. So I always put the I in between the number outside the radical and the number inside the radical. So here's what we currently have. We've got x equals negative 2 plus or minus, and then we simplified radical negative 80 to radical 4i radical 5 divided by 6. And I want to see what else I could simplify here. Now keep in mind that all of these numbers are divisible by 2. So if you wanted to rewrite this to try to think about how you could simplify this, you're dividing a negative 2 by 6, but you're also dividing a 4i radical 5 by 6. Well, this first part, I see that they're both divisible by 2. And if you didn't see that, just type that fraction straight into your calculator. You'll be able to simplify it immediately there. That negative 2/6 would simplify to negative 1/3 if I divide them both by 2. And if I divide the 4 by 2 and the 6 by 2, that would be 2i radical 5 divided by 3. So in simplest a plus bi form, that just means your imaginary parts in the back, your real parts in the front, would look something like this. Or if you wanted to write it as two solutions, negative 1/3 plus 2i radical 5 over 3, and x equals negative 1/3 minus 2i radical 5 over 3. So these quadratic formula problems are kind of like what you saw in Algebra 1, just the simplifying of the radical could look a little bit different if there's a negative under the radical. Even though I'm not going to do it, number 9 is the same exact scenario. Plug into the quadratic formula and simplify the radical as much as you can.